If a star exploded right next to you, you wouldn't hear a thing. A supernova releases more energy in a single moment than our sun will produce in its entire 10 billion year life. It can incinerate whole solar systems. Yet if one detonated close enough to fill your sky with light, it would happen in perfect silence. But to understand why space kills a sound, you have to look at what sound is. Think of it like a row of dominoes. When you speak, your vocal cords shove the air molecules right in front of your mouth. Those molecules slam into the ones next to them, creating a chain of tiny collisions, racing outward until the very last molecule nudges your eardrum. Now, take away the dominoes. Here on Earth, the air around you holds about 10 billion molecules in every single cubic centimeter. In deep space, that same volume might hold one stray atom. The dominoes are kilometers apart. There is simply nothing to knock into anything else. In a vacuum, a sound wave doesn't try to cross the distance and eventually run out of breath. It never even begins. Sound isn't a thing that moves through matter. Sound is matter moving. Without matter, you get absolute silence. But that strict rule of physics creates an immediate, glaring contradiction. If a vacuum perfectly blocks mechanical waves like sound, we should be entirely isolated from the rest of the universe. Instead, you feel warmth on your skin and see light filling the daytime sky. Starlight and solar heat arrive every single day. All of that energy is crossing 93 million miles of completely dead vacuum to reach us. So how can the empty fabric of space entirely smother the shockwave of a detonating star, while allowing sunlight to pour through as if the vacuum weren't even there? The answer splits waves into two categories. Sound needs a medium, but the electromagnetic spectrum works differently. It is self-carrying. Rather than relying on molecules, an electromagnetic wave builds its own way forward, an electric field generating a magnetic field, leapfrogging through pure nothingness. Because these waves cross the vacuum freely, they flood the universe. Almost everything out there is blasting these self-carrying signals in every direction, around the clock. The galaxy is crackling. Dying stars, spinning neutron stars, superheated gas swirling around black holes are constantly broadcasting massive amounts of energy across the void. If you could retune your senses to pick up that spectrum, the night sky wouldn't be a peaceful blanket of quiet lights. It would be the loudest room you have ever stood in. There is another type of wave that goes even further than the electromagnetic spectrum. We call them gravitational waves. To understand them, you have to drop the assumption that space is just an empty stage where things happen. Space is a physical fabric. And when two incredibly dense objects, like black holes, spiral into each other and collide, they hit with such violence that they make the fabric of space itself ripple like a struck drum. A passing gravitational wave wouldn't push on your ears. It would literally stretch and squeeze every cell in your body. By the time these ripples reach Earth from a billion light-years away, they are fantastically faint. Detectors at the LIGO facility capture them by measuring our entire planet wobbling by a distance thousands of times smaller than a single atomic nucleus. We built a machine delicate enough to feel two black holes collide on the far side of the universe. For the first time, we had an artificial ear sensitive enough to notice that the cosmos was ringing. So, if the universe is screaming in frequencies our biological ears can never catch, how do we listen in? We use deep space probes as giant roving microphones. This chart shows exactly how scientists manage that. They take raw, ultra-high electromagnetic waves pouring off the planets and shift their frequency down into our hearing range, translating invisible data into a sound we can play out loud. When you do this with Saturn, the radio emissions tied to its polar auroras produce a ghostly chorus of rising and falling whistles. It sounds like something breathing deep inside a cave. Jupiter is even more intense. As a spacecraft crosses the boundary of its immense magnetic field, the data translates into a deep oceanic boom, sounding exactly like a storm-tossed sea the size of a planet. None of this audio is faked or added for cinematic effect. These are the true, objective electromagnetic voices of those worlds, finally decoded for us to perceive. And we can listen even further out. Voyager 1 is currently drifting into true interstellar space, far beyond the planets. What it continues to record out there is a faint, persistent ringing. It's capturing the density of the galaxy itself, the thin haze of ancient gas left behind by stars that died before our sun was born. This tiny machine, built in the 1970s and running on less computing power than a modern smartphone, is out there in the absolute dark, patiently translating the hum of the galaxy and mailing it back to Earth. We do not live in a silent void. We live in an ocean of electromagnetic screaming. We are simply wrapped in a thin, accidental quiet because our bodies evolved specifically for a planet with air, not for the massive roar outside. Space isn't mute. The silence was never out there. The silence is us.